Welcome back to section 5 of chapter 4. This section is on a topic called related rates. Now, related rates is a fairly broad topic in that it covers a wide variety of different things. However, all of these problems are done basically the same way. We are going to be setting up an equation, usually a formula, involving a couple different variables. And then we're going to take the derivative with respect to time. Um, if we're looking at the um, the picture in the background here, actually, this is a related rates diagram because we have the derivative of y with respect to time, and we have the derivative of x with respect to time. That's going to be the speed that the y variable is moving in that direction, and the speed the x variable is moving in this direction. This problem is actually very similar to what our first problem that we're going to look at is, and that's a ladder problem. The ladder problems are an amazingly common archetypal problem for related rates. In fact, they're so prevalent that we have a theorem called the ladder theorem. Now, this isn't an official theorem like the mean value theorem or the intermediate value theorem or the Pythagorean theorem. But the ladder theorem says when working with real-world applications of advanced mathematics, it is obligatory to involve a ladder at some point, preferably one leaning against a wall. Specifically with related rates, it's not just going to be leaning against the wall, it's going to be sliding down the wall because that's what's going to give us a rate. We're going to have rates of change. If it's just leaning against the wall and it's not moving, there's no rate of change. There's no related rates. Um, and so what would a problem look like? A ladder problem would look like a 10-foot ladder leans against a wall. If the top of the ladder begins to slide down the wall at a rate of 2 feet per second, how fast is the bottom of the ladder sliding away from the wall when the top of the ladder is 8 feet off the ground? Just like with optimization problems, a lot of times one of the very first things to do is draw a picture and label it. So we have a ladder, it's 10 feet long. Our y variable, notice our y variable is going down and our x variable is going to be getting bigger. And the 10, the ladder's not going to change size. So that 10 is actually going to be constant. It's going to stay the same. So now we need a formula that relates this stuff. Pythagorean theorem, we're dealing with a triangle with 3 sides, a right triangle with 3 sides. So Pythagorean theorem, we have x squared plus y squared equals the hypotenuse, we'll call it L squared for ladder. So we're going to take the derivative of this, but first we want to look to see, do we have any constants that we can plug in? Now, this is a place where you have to be very careful. One of the mistakes people make is they plug stuff in too early, stuff that's moving. So here, x and y are both moving. That we can't plug anything in. However, the hypotenuse, that ladder, it's the same size. That 10 is a constant. So we could plug that in for L. So we're going to get x squared plus y squared equals 10 squared, or 100. Now we can take the derivative with respect to t. So just like when we're doing implicit differentiation, each variable is going to get like a dx or a dy, but with respect to t, it'll be a dx over dt, a dy over dt. So the x squared is going to be 2x times dx over dt plus 2y dy over dt equals 0 because 100 doesn't have a variable. So this dx over dt, that's how fast the x is moving. The dy over dt is how fast the y is moving. So we actually have those rates, or we have some of those rates. At this point, we know all of the values here except for one. We either know or we can find all the values except for one. So I would recommend figuring out what is that thing that you don't know so you can make sure you plug in everything else. So what is the thing that we don't know? What are we looking for? We're looking for how fast is the ladder sliding away from the bottom of the wall. That would be the dx over dt. That's what we don't know. We know all the other pieces. So we're going to have 2 times x, which is something, times dx over dt, plus 2 times y times something equals 0. So we'll plug in what we know. We know that it's sliding down the wall at 2 feet per second. So we can put that in. Now, a common mistake here is to put in 2. It's not actually 2. It's sliding down the wall. It's going to be negative 2. What else do we know? We know we want to know what's happening when the top of the ladder is 8 feet off the ground. That means we want y to be 8. So we're going to put 8 in. And now we just have to figure out what is x. Well, we're going to go back to the Pythagorean theorem. When y is 8, what is x going to be? You can plug it into the Pythagorean theorem, or hypotenuse is 10, one of the sides is 8. You probably already know that the other side is going to be 6. At this point, we're just going to solve for the dx over dt. So we have 12 dx over dt plus, and then the 2 times 8 times negative 2 is going to be a negative 32 equals 0. We can add the 32 over, divide by 12. So dx over dt is going to equal 32 over 12, or we can divide these by 4 to get 8/3 feet per second. Units are important here. These are rates. So this is a very, very typical problem. The ladder problem is very common, and it's nice. It has a nice Pythagorean theorem is an easy thing. We can see what's going on. We can see the when we take the derivative, how we get the rates. We're going to look at a couple more problems, but notice when we do them that they're all basically the same as this one. An oil tanker has an accident and oil pours out at a rate of 150 gallons per minute. Suppose that oil spreads over the water to a thickness of 1/10 of an inch. Given that 1 cubic foot equals 7.5 gallons, determine the rate at which the radius of the spill is increasing when the radius reaches 500 feet. So a lot of times people look at this and say, hey, we have a circle, an expanding circle, which is a very common type of problem. This isn't quite an expanding circle. This is the volume of a cylinder. How is a cylinder? It has a height. It's a very small height. This is a cylinder, just like a coin is a cylinder, or a pancake, a very, very circular pancake, is a cylinder. And so we have a height of that 1/10 of an inch. So we're dealing with volumes, we're dealing with cylinders. We're probably going to want the volume of a cylinder. So the volume of a cylinder is going to be the base, pi r squared, times the height. Now, we want to plug in the constants. The height is a constant, but we can't just go around throwing numbers in here. We need to make sure we're looking at the same units. Most of the stuff, we want 500 feet. Let's put stuff in feet. Our thickness, our height, is 1/10 of an inch. So we have 1/10 of an inch. We want to convert it to feet. So we're going to have to divide by inches, multiply by feet. We know there's 1 foot in 12 inches. So we can multiply. The inches here cancel. 1/10 times 1/12 is 1 over 120 feet. That's going to be the height. While we're doing conversions, the volume, it's actually the rate at which the volume is changing, is 150 gallons per minute. But gallons is not feet. So we want to convert that, and we know that 1 cubic foot equals 7.5 gallons. So we can start with 150 gallons per minute times, we're going to have to divide by gallons, multiply by cubic inches, and we know, or cubic feet, we just got rid of inches. 1 cubic foot, 7.5 gallons, and then multiply. 150 divided by 7.5 is 20 cubic feet per minute. And that's going to be the rate of the volume. This is going to be a dV over dt, because it's the rate the volume's changing. It's not the total volume, it's the rate the volume's changing. Well, now that we have the conversion, remember this is a constant. We can plug it in. So the volume is going to equal pi r squared times 1 over 120. Now we can take the derivative with respect to t. dV over dt is going to be, we're going to go pi over 120 times 2r dr over dt. And now we want to see, what are we looking for? We're looking for the rate at which the radius is increasing. So what we're looking for is the dr over dt, which means we should be able to plug everything else in. So we'll have something equals pi over 120 times 2 times something times dr over dt. Plug in what we know. The dV over dt we already saw was this 20 cubic feet per minute. The pi over 120 times 2, and the radius, we're looking for when the radius equals 500. And so we can multiply and divide. Multiply the 120 up, divide by the pi and the 2 and the 500, and this should get us 1 over 25 pi. No. Scratch that, that's the next one. That's what I get for trying to remember things. So we'll go 20 times 120 over pi. Come on, there we go. Pi times 2 times 500, which could be 1,000, I know. 5, come on, 0. There we go. Equals dr over dt. So we can start canceling stuff. That'll make that a 10, but hey, we can get rid of another 0, so that's 1. Get rid of a 0 there, so that's 12. So this would be 12 over 5 pi. Equals dr over dt. If we can't use a calculator. That would be our answer. It is an exact answer. A lot of times that's not a hugely useful answer, because what is 12 over 5 pi? Well, it's about 12 over 15, but that will simplify to about 0.76394 feet per minute. And so this question, our formula was different. We had some conversions to do, which isn't always a thing, but it's a thing enough that you want to be on the lookout for it. But the formula is different, but the process is the same. Plug in the constants, take the derivative with respect to time, and then plug in what you know to solve for the one variable that you don't know. Our next one's very similar, except we're going to be looking at a spherical balloon. And the nice thing about a sphere is it really only has one variable. It's the radius. Just like with the circle, but we had the height there. So here we have air is being pumped into a spherical balloon, so its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon changing when the diameter is 50 centimeters? So right away, the thing we need to be careful about here is the diameter, because the volume of a balloon is 4/3 the volume of a sphere. It's 4/3 pi r cubed. They give us the diameter. It's 50. Right away, r equals 25, so that we don't get caught by that trick. It's not a conversion so much, it's just not quite the right piece of information. So we're going to find it when r equals 25, but that's a moving variable, so we can't plug it in yet. Volume's moving, can't plug it in yet. So right away, let's take the derivative with respect to time. dv over dt equals 4/3 times 3 is just 4 pi r squared, which by the way is the surface area of a sphere. How cool is that? Then dr over dt. We're looking for how fast the radius is changing. That's that dr over dt, which means we should be able to plug in everything else. So the dv over the dt, how fast is the volume changing? Air is being pumped in at 100 cubic centimeters per second. So that's 100. The 4 pi, those are constants. R, we want when r is 25. So we're going to plug in 25. Divide to get dr over dt equals 100 over 4 pi times 25 squared. Simplify. 25 squared is just 25 times 25. I'm going to take one of those 25s times 4 to make 100. This is going to be 1 over 25 pi. That's where that 1 over 25 pi came from. That was on my brain last problem. But again, that doesn't necessarily help us out all that much when we're looking for how fast the radius of the balloon changing. Oh, it's about 1 over 75 centimeters per second. Yes, but what is that? What that comes out to be, and at this point it would be a calculator thing. The 1 over 25 pi is an exact answer. You can get up to that point without a calculator. Is that going to be an issue? Maybe. But on the AP test, definitely, you could do a problem like this on the no calculator part, and that would be your answer, 1 over 25 centimeters per second. On the calculator part, we're going to round it to a certain number of digits. We divide, and we get dr over dt is going to be about 0. That was the worst zero on the planet. 0. Nope, that one is. There's a win. 0.0127 centimeters per second. And so we just plug it in. Notice that problem didn't take all that long. It's only a couple steps. There's actually a couple steps there that we didn't even necessarily need to show. Um, and so these problems, they can be short. They could be long, but for the most part, there's not too many steps unless you have a whole bunch of conversions or something to do. Plug in your values, take the derivative, plug in the rest of the values, solve for your unknown. Those are the steps. There's only a couple of them. The tricky part is getting the equation in the beginning, especially when you have something like this, which has a story to go along with it. So a spectator at an air show is trying to follow the flight of a jet. The jet follows a straight path in front of the observer at 540 miles per hour. At its closest approach, the jet passes 600 feet in front of the person. Find the maximum rate of change of the angle between the spectator's line of sight and the line perpendicular to the flight path as the jet flies by. So, first step, draw a picture. Hey, look, there it is. Sometimes, especially when you have something that's really hard to explain, like this one's not the easiest one to explain, you'll get a diagram. And so we're looking at a couple different things. We want the maximum rate of change of the angle. That's that guy. We have the jet passes 600 feet in front of the person. That's this distance is 600. That's a constant. And then we have the path of the plane, this x, that's going that direction. And it's going that direction at 540 miles per hour. So this 540 miles per hour is going to be the dx over dt, because that's the rate that that's changing. So we have a right triangle. Pythagorean theorem. Except we're not looking at that side. We have two sides and an angle, which means we're going to have to use dun 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 trig. But that's okay. These are trig equations actually set up super easy in these because it's just SOHCAHTOA stuff. In this case, we have the opposite and the adjacent. That's tangent. So my equation, tangent of theta, is going to equal the opposite, x, over the adjacent, 600, which it's a constant, so I can plug it in. That was going to be my next step. But we can plug in 600 because it's a constant. So our two variables are theta and x. We can take the derivative. Derivative of tangent is going to be secant squared of theta, d theta over dt, equals 1 over 600. Derivative of x is just dx over dt. And now we can plug stuff in. We're looking for the d theta over dt. We don't know what theta is because that's going to be changing. So we'll leave that. The dx over dt, we want to plug it in, but 540 miles per hour doesn't really work because we're looking at 600 feet. And so let's change, instead of miles per hour, let's change it to feet. Instead of feet per hour, which is going to be a really, really big number, we can change it to feet per second. And so we're going to convert the miles to feet. We're going to convert the hours to seconds. And when we do that, we're going to end up that 500 miles per hour is equivalent to 792 feet per second. So let's plug that in because that'll match with the 600 feet and it'll help with the angle. I mean, when we're looking at this jet flying by, we're not going to want to measure in minutes or hours. We're going to measure in seconds because they're fast. So we have secant squared theta of d theta over dt equals 1 over 600 times 792, which we'll multiply those. That ends up equaling about 1.32. And then let's divide by secant squared. But dividing by secant squared is kind of weird because secant is 1 over cosine anyway. So instead of dividing by secant squared, let's multiply by cosine squared. So the d theta over dt is going to be 792 divided by 600, which is about 1.32 times cosine squared of theta. Now we're looking for the maximum rate. The d theta over dt is the rate. We all know when it's going to be the biggest. It's not a constant rate. It's not just 1.32 because that cosine's moving. But doesn't it make sense that the d theta over dt is going to be the biggest when the cosine squared is the biggest that it can be? And the nice thing about sines and cosines is the biggest they can be is 1. Cosine squared, the biggest this is going to be is 1, which means that the maximum d theta over dt is going to be 1.32 times 1, so just 1.32, not feet per second, degrees per second. So it's going to be 1.32 degrees per second. That's going to be how fast that angle changes, how fast you have to turn your head. And so it's the same as any kind of distance. It's just, ooh, we're looking at an angle. But it sets up the same. And notice the trig sets up quite nicely. There will be times when you'll have a value there where you can plug it in, like how fast is the angle changing when x equals 2? And you'd plug in the 2 and the 600, you'd figure out what that angle is, or at least you'd figure out the cosine squared of that angle, and you'd get a number. But in this case, we're looking for when is it the biggest? It's just when it's 1, which happens to be at this point right here, which if you think intuitively, it should make sense. That's when the plane looks like it's going the fastest, because after that you have an angle, and so it's not going directly in front of you. Anyway, that's related rates. We have just problems, and again, draw a picture, set up a formula, and then plug in your constants, take the derivative with respect to time, and then plug in everything else that you know to solve for the one thing that you don't know. So with that, keep working problems, keep asking questions, and as always, happy mathing.